In Chapter 13, we're going to look at carboxylic acids, esters, amines, and amides. As you read through the chapter, remember to do the index problems as you go. Now, the functional group that we find in organic acids are truly an acid. They're acidic because the proton can come off this functional group rather easily. It dissociates and it will make a proton in water. There are three different ways that we will write this functional group. We will write it as CO2H, or we will write it as C double bond O and then an OH attached, or we will write it out as COOH, and they all mean the same thing. This carbon is like a carbonyl with a hydroxyl group on it, isn't it? And it's acidic because the negative charge that results from the proton coming off is stabilized by the other oxygen that's on the functional group. So the carbonyl stabilizes the negative charge on the oxygen next to it. Carboxylic acids will react with bases, and this is a typical acid-base neutralization reaction shown here, except it's with an organic acid. Acetic acid is this specific acid. You can see that the acetic acid has on it a hydrogen that can easily come off as a proton, leaving a negative charge behind on the oxygen. What takes it off the acetic acid? Normally the proton will come off because it is acidic, but here the base hydroxide plucks the hydrogen off the acetic acid, leaving a negative charge behind. That gives us sodium acetate and water. The proton plus hydroxide gives you water, and then the salt that is made is sodium acetate. Remember that the product of an acid-base neutralization reaction is called a salt, and it is a metal with a nonmetal. And you can see here that this is a metal, sodium, with a nonmetal, acetate. Now it's written backwards from what you have seen in inorganic chemistry, and there we would have written the sodium first and then put the acetate afterwards. Sometimes in organic chemistry, to emphasize the organic portion of it, we'll write the acetate part first and then follow with the sodium. Notice the other product of this reaction is water, and it's formed by the proton from the acetic acid and the hydroxide from the base. The oxygen-hydrogen part of the functional group on an acid can hydrogen bond. They're just like alcohols in that they can hydrogen bond quite well. The acids can actually hydrogen bond to themselves, hydrogen bonding to each other, and they form a dimer that makes the molar mass twice as large. So you get a very high melting point and boiling point for acids. And it's due to them hydrogen bonding and two of them being stuck together. That's what a dimer is. Acids can hydrogen bond to water and to other molecules that have an oxygen-hydrogen bond. So this makes most acids water soluble as long as the number of carbons is not too high. 5 carbons or less, and the carboxylic acid is water soluble. Here are all the places where a carboxylic acid can hydrogen bond. This is what makes it relatively water soluble. You've got an oxygen on the carbonyl, you've got an oxygen on this what looks like an hydroxyl group, and you've got a hydrogen that can hydrogen bond. So that part of the molecule is very hydrophilic. They can hydrogen bond to each other. That's showing all the hydrogen bonding that can occur. There's actually even more that can be attached than just what I'm showing. Because of this hydrogen bonding, acids have a high melting point and boiling point. Because water can hydrogen bond in so many places, the carboxyl groups are very hydrophilic, and acids with up to 5 carbons are water soluble. To name acids, what we do is we count the longest chain that has that functional group. So you take the alkane name, then remove the E and add oic acid on the end. You have, just like with the aldehydes, the acid functional group, the carbon in that acid functional group, is always the number 1 carbon. Now when counting the chain, be sure and include that carbon in the carboxylic acid. That's a common error for students to neglect to count that when counting the longest chain, but it is in the chain even though it's part of the functional group. After getting the chain and the ending correct on the molecule, then you're going to find all the substituents, name them, and number them, and remember to place them in alphabetical order. Always use the numbering system that the functional group sets. So the number 1 carbon always remains the number 1 carbon even after naming and numbering the substituents. If you have a carboxylic acid attached to a benzene ring, then those are called benzoic acids. There's only one common acid name to know, and that's acetic acid. We've seen it before, and you probably remember us referring to acetate, which is acetic acid with the proton taken off. The systematic name is ethanoic acid because 2 carbons gives you the ethane, then you take off the E and add the oic acid. Acetic acid is what we almost always call it, unless we're trying to be really official. If you look at these 2 compounds, we can name them. We find the longest chain in the top one, and you can see there are 1, 2, 3, 4, 5 carbons. So that's pentanoic acid. Notice you start, the number 1 carbon is going to be the carbon of the carboxylic acid group, the COOH, and then 2 is the CH2, 3 is the CH, 4 is the CH, and then one of the methyl groups is the 5th carbon. We then name and number the substituents. Number 1 is the carboxylic acid, so number 3 would have the methoxy group on it. Number 4 has a methyl group on it. To name this compound, we see that it is a benzoic acid. Benzene, this would be called benzene, but with the carboxylic acid group on it, is then called benzoic acid. And you can see that attached to the benzoic acid, the number 1 carbon would be where the carboxyl group is. Attached to the benzoic acid, you have an ethyl group on the number 3 carbon. Another way of referring to this is meta-ethyl benzoic acid. So now what I'd like you to do is try to draw butanoic acid and try to draw this compound down here. Remember that when hydroxy is a substituent, we just call it a hydroxyl group. So try to name and number that one. Okay, to draw butanoic acid, the first thing we see is the but, so we know we need to have 4 carbons. With the oic acid, we know we need to have on the number 1 carbon the carboxylic acid group, which we have here, CO2H. If you wrote it as C double bond oxygen, then dash oxygen hydrogen, that would have been fine also. And some people do write carboxylic acids as COOH. It's not quite as common as CO2H. For this compound below, we can see the longest chain has 3 carbons in it. So that's going to be propanoic acid. Then we see there's a substituent. That substituent is a hydroxy group. So we say 2-hydroxypropanoic acid. Why did I draw this particular structure? It's because I wanted you to see that some of the things that we hear about, like lactic acid or glutamic acid or any of these other things that we see in biological chemistry, we'll see they often end in acids. That's because they are carboxylic acids. This is a carboxylic acid. Lactic acid also has a hydroxy group on it. If it didn't have that hydroxy group, it would just be plain propanoic acid, but because it has the hydroxy group on it, we call it 2-hydroxypropanoic acid.